All right, guys, one last video tonight attacking this question. So I enjoyed writing this question, honestly. It's very heavy. It's going to touch on a lot of things. If you attempted this question and got every aspect of it right, then huge props to you. You've been staying on top of your work at least as long as I've been here this semester or this quarter at least. And somebody who was able to attack this well. So let's look at what's going on here. We have an initial value of an isotope decaying by emitting a helium nucleus, and it has a half-life of 6 hours. Okay, so we're given a lot of info in that one sentence. Okay, answer the following questions. First of all, how many neutrons does americium, americium 241 have? Alright, so let's flip open our periodic table here and find it down in the actinides. Okay, so it has 95 protons. Okay, so americium 241 with 95 protons. So figure out how many neutrons it has. Well, the nucleus is made up of protons and neutrons. Electrons don't have mass, so protons and neutrons are the only ones that contribute to atomic mass. So if we take 241 and subtract 95 and subtract the number of protons, which is the atomic number right here, if we subtract that from the number of protons and neutrons, then we're left with just the number of neutrons, which is what this part of the question is asking us. So 241 minus 95 equals 146. So the answer to A is 146 neutrons. That's how many neutrons are in this element. Okay? So that's how many neutrons are in this isotope. I believe it is less than it normally has, so that's just one thing to note. Let me see. Yeah, it's less than normal it has. So a lot of times we deal with isotopes that have more neutrons. In this case, it has less neutrons, and it's still going to decay because it wants to get to something more stable. And less neutrons is not more stable than what normally be. Okay, so it's emitting a helium nucleus. So let's see. Let's make this thicker. So now we're attacking part B. It's way too thick. We're gonna roll with it though. Okay, what symbol for the decay that's occurring? So what do we know about the decay? We know it's decaying by emitting a helium nucleus. Okay, so if it's emitting a helium nucleus, it looks like this. What do we call this? Well, we go way back up here. We call it an alpha particle. Okay, so this right here is an alpha particle. It's undergoing alpha decay. And it asks us what's the symbol for the decay that's occurring. Well, it's a Greek alpha. That's a pretty ugly one. It's not pretty either. Whatever, you get it. Alphas. Alphas all around, okay? And alpha is the symbol for the decay that's occurring. Okay, we're through A and B. Let's take a look at, oh boy, C. All right, so what's C asking us? What is the isotope turning into? Okay, so now we need to figure out what element it's becoming. So we have americium 241, americium, I don't know if I'm saying that right, I really don't. Not an element we look at commonly. Anyway, we have this decaying, and we know that's giving off a helium nucleus. Okay, and now we have to figure out what the next element is. So if it's giving off a helium nucleus, that means the atomic number is dropping by 2. 95 minus 2 is 93. It's going to be down here. And then the atomic mass is dropping by 4. 241, 237 here, okay. So we know that the atomic number is 93. So pop open our good old periodic table again. We said 93 is NEP neptunium, NP. So that is what it's decaying into. It's decaying into neptunium-237. Okay, losing 2 protons and the atomic mass is dropping by 4. So this is what the stable or more stable product of this decay is going to look like. Okay, now lastly, D, so I'll just put a D here. We're being asked how many grams of the stable material will be left after 78 hours. Okay, so again, we're trying to figure out how much of something is left after a certain amount of time. However, one thing I want you guys to notice here is asking stable material. And I could have been more specific. I could have said the more stable material, something like this, but hopefully it was clear enough to tell you guys that I'm not asking for how much of the isotope or the radioactive isotope is left. I'm asking how much of the stable, what it's decaying into, neptunium-237 is going to be left after that amount of time. I guess I could have worded it by saying how much is going to be created, but again, I hope that was clear enough for you guys. So our first thing is just to solve it like we normally would, and then we'll figure out the other part. So we have, just to write the whole equation again, our amount of isotope is equal to our initial amount multiplied by 1/2 raised to the n power. Okay, so we have our initial amount here, 762 milligrams. And our number of half-lives, I'll write that right here, 162 milligrams. And our half-lives, let's see, we have, has a half-life of 6 hours. We're told it asked how much is left after 78 hours. So 78 divided by 6. Let's take a look here. I don't know that off the top of my head. 78 divided by 6. 13. Oh my goodness. I've dropped my pencil. 78 divided by 6, 13. So it underwent 13 half-lives. So we're multiplying 762 by 1/2 raised to the 13th power. Okay. So this is where I really wish I had brought my calculator home, because let's try and do this now on my iPad calculator, which I downloaded today. So let's see here. There we go. Okay. What? Jeez. There's probably a way to do this that you guys see, but I don't. Oh, lit. Okay. Ew, I just cringed at myself the way I just said lit. Oh, lit. That was gross, huh? Okay, so we'll do 0.5 raised to the 13th power equals, wow. Okay. 3 zeros, 1, 2, 2. Okay. So this value right here is 0.12312. 2 zeros, 1, 2, 2. We'll leave it there. I'm going to multiply that by 762 milligrams. Okay. I'm going to do that math on my calculator on my phone right now. So 762 times 0.000122. Okay. So that gives us 0.09296. Okay, but let's look at sig figs. Here we have 3. Okay, so we're going to round to 3 here as well. That means that this goes up to 0 and that goes up to 3. So 0.0930. Okay, so And our units here are still milligrams. So what do we know now? Normally this would be it, but we're not done. Right now we know this is how much of the isotope, the radioactive isotope, remains. So how much of the stable product remains? Well, if you recall from the very first time we talked about half-lives, I tried to emphasize the fact that nothing just disappears out of existence entirely. So whatever you started with is how much your end product is going to weigh still. You're just going to have decayed into something new. So you started with 762 milligrams, and now all that you have left of your americium-241 is 0.0930 milligrams. I know I didn't line that up well, but that's okay. So if we subtract the amount that's decayed from the total, the amount that's left from the total, then we're going to be seeing how much the radioactive or the stable isotope is still there. So minus 0.0930 761.907 milligrams. So it's pretty much entirely now neptunium-237. And let's see, for sig figs, we have 3 in each of these, so we're only keeping 3. So we say about 762 milligrams. Okay, that's how much neptunium-237 is going to be left. But wait, there's more. I said how many grams? Okay, so that's fun, right? How many grams? Okay, so let's do a quick conversion. 762 milligrams. And if you didn't catch that little snippet, I would encourage you to stop this video and try it yourself first, because that is what is going to allow you to learn. So we have milligrams here. Now let's set up our conversion. So we know that we're going to multiply by some conversion factor to get an answer in grams. And I'll highlight grams in, say grams are green. Okay, grams are green. So our conversion factor that we're going to have to set up here. How are we going to change milligrams to grams? So we want to get rid of milligrams, and if you want to get rid of something, drop it like it's hot, drop it like it's hot. So that's going to go down here, milligrams down here, still in orange. Okay, and that means that grams, to get our answer in grams, has to go up here. Grams are green. Okay, so now what is our conversion factor? How many milligrams are in 1 gram? Well, there's 1,000 milligrams in 1 gram. 10 to the third. 10 to the third milligrams in 1 gram. So that means we're looking at 762 divided by 1,000. Okay. 762 divided by 1,000. Divided by 10 to the third. So we're just moving the decimal. And we're going to get point. I don't know if I'm going to have enough room here. How can I fit this in? Let's see here. 0.000762 grams. Okay, and we can write that scientific notation as 7.62 times 10 to the 4th grams. Okay, and this would be your final answer in grams. And does it make sense? We're going from a small unit of measure to a larger unit of measure. So we're measuring the same thing with fewer units. So you can even think of it as, obviously this isn't distance, but if you have something and you're measuring it with units that are this long and it only measures to 3, and then you measure it in units that are much shorter, you're going to have a lot more units in the one that's shorter. So the number will be larger for these ones and smaller for these ones. Grams are a larger unit than milligrams, so we expect to have a smaller number measuring it. So it does make sense that our number becomes a small decimal with 10 to the negative fourth on it. Okay, that might have sounded a little confusing, but I'm just trying to say that our answer makes sense. We've eliminated milligrams through our math, and we're left with the answer in grams. Okay, so that was a long question with a lot of parts to it, and a lot of things that you had to catch in the question itself to get it completely right. But if you, like I said at the beginning of this question, if you were able to go through this and systematically work through every aspect of it and get the correct answer, if you got everything correct in this, I would be extremely impressed. If you at least were doing the math correctly and maybe missed the conversion, or you missed the sig figs, but you're doing all the math correctly, great job. And thank you guys for watching this. Thank you for working hard, and I'm sure you're going to kill the test.